This first section of problems is just a matching section, but that's good practice for our AP exam. We'll likely have a problem where we have to pick the correct graph or pick the correct equation to match what's given. So I'm going to begin just by looks like each of these functions have unique denominators, except for these two. So I'm going to begin just by looking at the vertical asymptote, finding where the gap is, and seeing which one matches up. So this one should have a vertical asymptote at x equals -2. And if I look at the first graph, that's the only one that looks like -2 is an option. So A has to go with number 11. And then if I go over to number 12, x equals 3 needs to be that vertical asymptote. So 1, 2, 3 is right here, which I don't think is right for B. So 1, 2, 3 is right here. That looks to be where the gap is. And I don't see, again, any others with a possibility for x equals 3. So D has to go with 12. Now 13 and 14 both have x equals 0. So that's narrowed down to C and E. So then the next thing you look at is the next thing I would look at is the horizontal asymptote. So 13 has to be y equals 4, which would be 1, 2, 3, which would have to be this one for a horizontal asymptote compared to this one, which is at -1, which matches 14. So C has to go with 13 and E has to go with 14. And then we have a vertical asymptote x equals 4 for 15. That's got to be B. So by default, that leaves us with F for 16, but we can just verify it should have a vertical asymptote at x plus 4. This negative doesn't affect that vertical asymptote. Even if you distribute it through the bottom, -x minus 4 is still x equals -4 for the vertical asymptote. Okay, in the next section it says find all asymptotes of the graph of the rational function. I'm not going to verify with a graphing utility. If you need practice um, typing in these rational expressions and graphing, then I would encourage you to do that with your graphing calculator, and you can check to see if you're right with Desmos if you're not sure if you're typing it in correctly. Or come to office hours and we'll get that straightened out. All right, so I'm just going through the three types. We have vertical, horizontal, and slant asymptotes. Vertical asymptote for number 17 is x equals -1. Horizontal asymptote, it's bottom heavy, so y equals 0. If there's a horizontal, there can't be a slant, but remember slant is top heavy by degree 1. So none of these have slant asymptotes. I just wanted to make sure that I reminded you that they exist. At the end of the assignment, we'll find some slant asymptotes. For number 18, the vertical asymptote is x equals 2. This again is bottom heavy, 3 over an x cubed, so y equals 0. No slant. For number 19, you've got to do a little bit of factoring to make sure you get the proper vertical asymptotes. This one has 2. There's one at x equals -3 and x equals 2. It's a tie as far as horizontal asymptotes. We've got 2x squared over x squared, so y equals 2 over 1, or just y equals 2. And again, no slant because it's not top heavy by a 1 degree difference. And our last one, it kind of looks like stuff should cancel, but if you look at this, you factor out an x from the numerator, you get x minus 4. And remember, x squared minus 4 is x plus 2, x minus 2. So I was double checking that to make sure that there were no holes. The vertical asymptotes are at x equals plus or minus 2. And I like to go to the non-factored version to figure out the horizontal asymptote. This is a tie, so y equals 1. And no slant asymptote. In the next section, it says find all asymptotes and holes in the graph of the rational function. Again, I'm not going to use the graphing utility to verify, but you could. So what you should be doing here is factoring and simplifying the f of x that they give you as much as possible. So I can take an x out, and I can cancel these x's, but 2 plus x does not reduce with 2 minus x. So vertical asymptote is when in the simplified function, whatever survived simplification, I say, becomes a vertical asymptote, so x equals 2. The whole is what got simplified out, so there's a whole at x equals 0, but remember you're supposed to find the ordered pair for the whole. So find f of 0, and last thing to remember, if you plug it into the original, you're going to get 0 over 0, which is not 0 and it's not undefined. It's called indeterminate form. More on that in calculus. All that means is you needed to simplify it, see what you were looking at here. So plug 0 into the simplified function and you get 2 over 2. So there's a whole at the ordered pair 0, 1. That point is not on the graph, it's a discontinuity. And then horizontal asymptote, whether you look at your simplified version or the unsimplified version, it's a tie either way, and you're getting 1 divided by -1. So y equals -1, it's the horizontal asymptote there. For 22, we can factor the numerator into x plus 1 squared. Denominator has to be 2x and x, and then 3 and 1 to get -1 in the middle, so -3, +1. That'll give us 2x minus 3x. We can divide out a pair of x plus 1s, and that leaves you with x plus 1 on the top, 2x minus 3 in the bottom. So because there's no longer an x plus 1 in the denominator, that's going to become the whole. There's a vertical asymptote at x equals 3 over 2. The whole is at x equals -1. And again, I want to find the heights, the actual ordered pair for the whole. So plug f equals plug -1 into f of x, the simplified version. So -1 plus 1 over, plug in -1, -2 minus 3. You get 0 over -5. 0 over any non-zero number is 0. So there's a hole in the graph at -1, 0. What that means is, even though we might say we might first find that there's an x-intercept at -1, actually that's a hole in the graph. And horizontal asymptote, this is a tie, y equals 1/2. For 23, I can factor the difference of squares in the numerator. I can factor out a GCF of x in the denominator, which shows me I can cancel out x plus 4s. So the simplified function is x minus 4 over x. That means there's a vertical asymptote at x equals 0. There's a hole at x equals -4. And then find f of -4 by plugging into the simplified version. Should do that little arrow for each of these. So -4 minus 4 over -4. That's -8 over -4, which is 2. So there's a hole at -4, +2. And for the horizontal asymptote, this is again a tie. It's 1x over 1x. So y equals 1. 24. Now, if you want to, for 24, the x squareds in the numerator, the x squared is negative. If you want to factor a negative out, you can. I think I'm just going to do it backwards. Some people can't quite wrap their brains around the backwards aspect. So you're trying to get 14 in the middle. So if you want to factor out the negative, go ahead. And then that makes it 5x squared plus 14x minus 3. And you would just have like a negative out here. All right, so I need -14. So I'm going to do -15 plus 1x. And then the denominator doesn't have to be backwards. Those are all plus signs, but I don't know. I'll just keep with my backwards theme here. Break up 2x into 2x and x, because I want to get 7x, so 6x, 1x. And they're both positives. So I can cancel out some x plus 3s, and this is 1 minus 5x over 1 plus 2x. All right, and so there's a vertical asymptote at x equals -1/2. The whole was at x equals -3. And of course, we're plugging -3 into the simplified function. So when you do that, you get 1 plus 15 over 1 minus 6. So 16 over -5. So that whole is at -3, and then -16/5. And if I'm plotting it, I'm thinking of that as -3 1/5. And then for the horizontal asymptote, This is a tie again, and when you divide out the leading coefficients, you get -5/2. Make sure, I should have said this earlier, but for all of your asymptote equations, they need to be equations. You cannot just write the number -5/2. You would not get any AP credit for that, and I would not give you credit for that either because it clearly says equations. We're not just tossing numbers out on the page. You got to say what they are. For this next section, A is find the domain of F. B is decide whether F is continuous. And C, we're only doing part of C. Identify horizontal and vertical asymptotes. We're not going to verify graphically or using a table of values. Again, you can if you want the practice, but I don't think that that's required. All right, domain. This takes us back to chapter 1. When we talked about domain, it was for rational functions. You need to just ensure that your denominator is not equal to 0. So for all of these, I should be looking at what makes the denominator equal to 0, or set it not equal to 0, I guess is what we said. And x squared minus 4 is always positive. If you try solving, you should get imaginary answers. So domain is just what are the real number restrictions on x. So this just means there are no real restrictions. The domain is all real numbers. We can plug anything into x squared plus 4 and we'll never get 0. That's all that says. And so because the domain is all real numbers for part B, that means that f of x is continuous. And so I'll just say why. F of x is continuous since domain is all real numbers. Part C is to go ahead and find the vertical and horizontal asymptotes. I, again, just wanted to throw in slant asymptotes just to remind you that you should be on the lookout for them, but none of these equations are top-heavy, so not an issue. So vertical asymptotes, well, if there are no domain restrictions, if there are no real numbers that make the denominator equal to 0, there are no vertical asymptotes. But there can still be a horizontal asymptote. This is still a tie, so y equals 5. This graph does level off. And then no slant asymptotes because it's not top-heavy. For 26, we're trying to figure out for domain what makes x squared plus x plus 9, set that not equal to 0. This doesn't factor, so I'm going to start the quadratic formula. And it's not about simplifying the quadratic formula as much as possible. You can stop once you recognize that you're going to get 1 minus 36 underneath the radical, and that's not real. And when we're talking about domain restrictions, we only care about real number restrictions. So x squared plus x plus 9 must always be positive for all x values. That means that the domain, again, is -infinity to infinity. And that means that for part B, determine if f is continuous. Same conclusion as before. If the domain is all real numbers, that's the same as saying there are no discontinuities. So f of x is continuous since domain is all real numbers. If the domain is all real numbers, again, there is no vertical asymptote. We do have a horizontal asymptote. This is a tie again, so y equals 3. And no slant asymptote because it's not top-heavy, and you can't have both a horizontal and a slant asymptote. Those two things guide the end behavior of the rational function, so you can't have both. Okay, for 27, I'm just noticing that the numerator can factor a bit, so I just want to kind of double check on 27 that I don't end up with any holes. So this would be x plus 4, x minus 1, and this is a difference of cubes. I'm looking at it as 27 minus x squared, so 3 minus x, and then I'm not sure if we've talked, I'm sure, actually I am sure that we've talked about this before. In a difference of cubes, that SOAP formula, this is always something that's going to give you an imaginary, it's prime, it's going to give you an imaginary solution set. If you do quadratic formula for it, that's how the sum and difference of cubes problems work. So you don't have to worry about that when you're trying to solve for the zeros. So anyway, nothing canceled. for part A to figure out when is this equal to 0. So really, I guess all of that is to say, I don't need to factor a sum or difference of cubes. I can just cube root knowing that I'm solving for the real number answer only. And remember, when you cube root, it's not plus or minus. The answer is just 3. Because -3, if you cube it, is -27, not 27. So this domain has a restriction, -infinity to 3, 3 to infinity. And because there's a domain restriction, the question to determine whether f of x is continuous, f of x is not continuous at 3. It's continuous everywhere else. There were no holes in the graph. There's just this one asymptote. So I'm going to say f of x is not continuous at x equals 3. Usually when you're talking about continuity, you have to identify where the discontinuity is. And so that brings us to asymptotes. So this one does have a vertical asymptote at x equals 3. The horizontal asymptote, going back to the problem here, it's bottom heavy, so y equals 0. And there's no slant asymptote since it's bottom heavy and not top heavy. Okay, number 28. We can't factor the numerator, so I'm not going to worry about that. So I'm just going to set the denominator equal to 0. I know I could factor out a 3, but again, it does not matter. Subtract 24 divided by 3. Remember, you don't have to factor this if you're just trying to find when it's equal to 0, because here you can just cube root. Cube root of -8 is -2. So the domain is -infinity to -2 and -2 to infinity. When I keep forgetting my union symbol, I'm not going to count off for that. It's not something that is really that important of a detail for our AP course. This means that f of x is not continuous, or you could say has a discontinuity. Oops. I said a word and started writing it down. Is not continuous. Gosh. At x equals -2. That's because there's a vertical asymptote at x equals -2. The horizontal asymptote, this one's a tie. So y equals 4/3. And no slant. Okay, our last section is on page 158. So for this, I don't want you to sketch the graph because that's what we're doing tomorrow. So instead, I only want you, for these graphs, to find the slant asymptote equation. And then we'll probably, as part of our homework tomorrow, sketch these graphs. So for all of these, you should be doing long division and finding the slant asymptote equation. Remember to throw out the, or ignore the remainder. So when you set this up, I'm dividing x into 1 minus x squared, but put in the correct order. -x squared plus 0x plus 1. I would multiply x by -x to get -x squared. Subtract, drop down the next one. I would multiply x by 0 to get 0x. Bring down the next one. That's a remainder. So the answer is not y equals -x plus 1 over x. In the long run, as you head toward infinity, you're going, like if you plug in a billion, you're going to get y equals -1 billion plus 1 over 1 billion. Well, that's practically plus 0. So for our slant asymptote, we just say y equals -x. Ignore the remainder. For 50, x squared, put in a placeholder plus 0x minus 1. We're dividing that into x cubed, but again, you want these placeholders just to make sure everything lines up. So I multiply x squared by x to get x to the third, and then I distribute that through. Subtract everything. So 0, 0, positive 1x. But that's a degree lower than what I'm dividing by, so that would be a remainder. But my slant asymptote equation is ignoring the remainder, just y equals x. For 52, x squared plus 0x plus 4, put in the placeholder. We're dividing that into x cubed, but again, I want to keep my placeholders here just to make sure. I multiply x squared by x to get x cubed. So that's going to be x cubed plus 0x squared plus 4x. Subtract 0, 0, negative 4x. That's a remainder. Ignore the remainder. This is another slant asymptote of y equals x. Last problem. 4x squared plus 0x plus 4. We've got negative x cubed plus 0x squared plus 0x. This one has a plus 3 on the end. What do you multiply 4x squared by to get negative x cubed? We definitely need the x, right? How do you get 4 to be negative 1? If you multiply it by negative 1/4, that would become negative 1x cubed, right? Remember, you can also always just do this. We're just dividing. Just divide and simplify. You get negative x over 4. So same idea. When you multiply that through, you get negative x cubed plus 0x squared. And then negative 1/4 times 4 is negative 1. 0, 0, 1x plus 3, but that's a remainder. Okay, so slant asymptote is y equals negative 1/4 x or negative x over 4. We ignore the remainder piece. All right, that's it for today's homework. Tomorrow we will be working on putting this stuff together to graph. So please come to office hours if you have any questions.